Today we start about application of Hahn Banach Theorem. One important theorem in functional analysis, Hahn Banach Theorem. We now start application part of this theorem. Application part we first discuss generally and then gradually we forward it. First we start this one. Let y be a subspace. Let y be a subspace of X, and f y to k be a continuous linear functional. Be a continuous linear functional. Then define fx to r. Then define fx to r by px equal to norm of f norm of x for all x belongs to x. Okay, we define this px, which one is the sublinear functional, and then going to forward discussion about that. And observe that what we observe now. So observe that first, px greater than equal to 0 for all x belongs to x, because here mod functions and obviously this one is greater than 0. Now to p of alpha x equal to what we write now, p of alpha x equal to here norm of f norm of alpha x. We know about that. This one equal to mod of alpha norm of f norm of fx. This one equal to mod of alpha p of x. Okay, then if alpha greater than 0, then p of alpha x equal to alpha p of x. That means pb for all x belongs to x and alpha belongs to k. Here then pb homogeneous. Okay, next we discuss about third part. Which part? This one, p of x plus y equal to what we find, norm of f norm of x plus y. Then next what we find, norm of f norm of x plus norm of y. This triangle inequality, this equal to what, norm of f norm of x plus norm of f norm of y. This equal to what, this equal to p of x, this equal to p of y. Then what we get p of x plus y less than equal to px plus py. Then p be sublinear. Okay, then p be sublinear. So we find that, we tell about that p be sublinear. Obviously we check another property of p. This was one important property. If px equal to 0, then what we find for x belongs to x, then what we find, this implies that norm of f norm of x equal to 0, then x may not, this implies that x may not be 0, always. Okay, then pb semi-norm also, okay. So we get this properties of p. We also obviously see about that. Next we erase for our portion and going to further discussion about that. Okay, so for what we discuss about now, we'll also extend this portion so easily. Now we discuss about all these assumptions of Hahn Banach theorem are satisfied. That means all these all the assumptions of Hahn Banach theorem of Hahn Banach theorem be satisfied. Okay, then what we do? We do we get from therefore there exists a linear functional, therefore there exists a linear functional which obviously extend this domain. That means we write this one f tilde on what x, on x such that f tilde x equal to fx for all x belongs to y, and f tilde x less than equal to px, this sublinear function for all x belongs to x. Okay, then what we talk about now? We talk about next thing. We talk about boundedness of f tilde. Okay, that means this one, obviously this one satisfies that f tilde is bounded by or dominated by px, this sublinear functional. But what we properly known about that, we discuss these things now. Now we talk about boundedness of f tilde. How we discuss so easily. We learn about that if delta x less than equal to px by Hahn Banach theorem. We use this Hahn Banach theorem here. Then obviously px equal to define this one. We define in this way, so we get this one. Next, what this one it gives? This gives that this one for all x belongs to x. Then this implies that hence if delta be bounded with norm of if delta less than equal to norm of. Okay. Next what we done? We done another way. We known about that norm of if delta equal to supremum of if delta x belongs to x and norm of x equal to 1. Then what we do? Greater than equal to supremum of f delta x. Okay, x belongs to y, norm of x equal to 1. This equal to supremum of mod of x, x belongs to y, and norm of x equal to 1. This equal to norm of. Okay, this one marked as 2. Then this one marked as 1, this one marked as 2. What we get? We get from 1 and 2. From 1 and 2, we get norm of f tilde equal to norm of. Okay, so we choose a function which obviously which satisfies Hahn Banach all this assumption of Hahn Banach theorem, and we construct one sublinear functional which denoted by norm f norm x px equal to, and then what we find? We find that this extension function or functional, obviously this extension functional norm equal to this norm of f. Okay, so we do something about that. Next we're going to further another application of Hahn Banach theorem. Okay, so we erase all this portion and going to further discussion of another problem. Now what we do? We write here first. Let Y be a proper closed subspace of a non-space X. subspace of a norm space X. Okay, and x0 belongs to x and x0 belongs to x with d equal to distance of x0 y. Obviously d equal to infimum of x difference x0 where x belongs to y. Obviously greater than 0. Then what we find? Then there exists a belongs to b x a such that first one fx equal to 0 and and f of x0 equal to b for all x belongs. And number 2, norm of f equal to 1. We have to prove that. We write this conclusion. Now we prove this formula. How we prove it? We go to step by step first. Let y0 equal to x plus alpha x0. Okay, x belongs to y and here alpha belongs to a. Then what we get? We get y0 be a subspace. Then we get y0 be a subspace of x. Subspace of x. And define now we define if such that x to k by f of u equal to f of x plus alpha x0 equal to alpha d for all x belongs to y and alpha belongs to. Okay, now we now show that f be continuous linear functional of y0. What we show? We now show that we now show that f be a linear functional. Okay, on y0. Obviously continuous linear functional on y0. Now first here we continuous linear functional. First we show that linearity of it. Linearity of it. So what we do? So simply we let here let u equal to x plus alpha x0 and v equal to y plus beta x0. Okay, x y belongs to y and alpha beta belongs to. Then and mu equal belongs to r or k you write it. Then what we do? Where is our portion? Then we do this one f of u plus b equal to what? F of x plus alpha x0 plus here y plus beta x0. Then what we do? We write here f of x plus y plus alpha plus beta multiplied by x. Then what we get from here? This one equal to alpha plus beta d. Then this one equal to alpha d plus beta d. This one equal to alpha d equal to f of u and beta d equal to f of and f of mu u equal to f of mu x plus alpha x equal to f of mu x plus mu alpha x equal to what mu alpha d. This equal to mu multiplied by f of u. Then what we get? We get f, hence f linear. Hence f linear. Passage so about that f be linear. Okay. Now we're going to further. Now we're going to further discussion about that. F of x0 equal to f of 0 plus 1 x0 equal to d greater than 0 and f of x equal to f of x plus 0 x0 equal to 0 for all x belongs to y. Then f is a non-zero linear functional always. Then f be a non-zero linear functional on y. Okay. Then we discuss about boundedness of f. Okay. Boundedness of f. How we discuss this one? Boundedness of f. Norm of f u equal to f of x plus alpha x equal to norm of alpha d for all x belongs to y and alpha belongs to y. Okay, now we have the following cases. Here is our portion. What we get now? Case 1. We have the following cases. We have the following cases. Okay, what we do? Case 1. Case 1. If alpha equal to 0, in this case, if u equal to f of x, norm of f of x equal to 0, norm of u less than equal to norm of u for all u belongs to 1. Case 2. If alpha not equal to 0, then let x belongs to y, and x by alpha belongs to y. Now norm of fu equal to f of x plus alpha x zero. This one now. This one equal to norm of alpha 2. This one equal to norm of alpha infimum of x minus x 0. X belongs to 1. This one equal to norm of alpha infimum of minus x by alpha belongs to y. Norm of x by alpha minus x. Okay, then what we get less than equal to norm of x plus alpha x equal to norm of t. Okay, so in respect to x, we put x multiplied by alpha. This one obviously belongs to y. X belongs to y, x by alpha belongs to y, so minus x by alpha obviously belongs to y. So we put here. Okay, not any problem in this way. So just next we talk about next just write here. Thus if norm of f u equal to norm of f of x plus alpha x less than equal to norm of u for all u equal to x plus alpha x belongs to y0. Hence f is bounded with norm of f less than equal to 1. With norm of f less than equal to 1. Okay, now we're going to further discussion about that. Case 1 obviously shows that norm of f less than equal to 1. Here obviously shows that norm of f less than equal to 1, and here also this one. Next we're going to hence f is bounded and with norm this one. Then what we do? We do by definition of norm of f, by definition of by the definition of norm of f, norm of f u less than equal to norm of e, norm of e. This implies alpha d less than equal to norm of e multiplied by x plus alpha x 0 taking alpha equal to minus 1. Then what we get? We get so simply d less than equal to norm of a norm of x minus x. Okay, this equal to norm of a infimum of norm of x difference is this equal to norm of a. So this implies that norm of a greater than equal to 1. Okay, now we're going to further discussion about that. Here we mark it as 1. Here we mark as 2. Hence we get norm of f equal to 1. Okay, hence by Hahn Banach Theorem, there exists f belongs to bxa with this one hold. Okay, then so what we find right now, I erase this portion. We find that then by Hahn Banach Theorem, we get there exists f belongs to bxa such that first fx belongs to or fx equal to this fx for all x belongs to 0, and that is f of u equal to f of x plus alpha x0 for all x belongs to y and alpha belongs to p, and f x equal to 0 for all x belongs to y, and f(x) equal to f(x) for all x belongs to y, and f of x0 equal to f of x0 equal. Now second, norm of f equal to 1. Hence, 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 let y be of a closed subspace of a norm space of a norm space x, and let x0 belongs to x difference y with b equal to continuum of norm of x difference x0 where x belongs to x greater than 0 obviously, then there exists a belongs to bx such that first one f(x) equal to 0 for all x belongs to y, and f of x0 equal to b, and norm of a equal to 1. Okay, we get this. So we discuss about two important formula. We also deal about that and getting knowledge and application about Hahn Banach theorem. That means we use Hahn Banach theorem here and getting something new, that means new function we construct and his extension also construct. Some functional and its extension also we construct. Next, we discuss that means some corollary, about those two applications. So which corollary says we write this corollaries now. First corollary, corollary 1, let x belongs to x, then there exists a belongs to bx such that fx equal to norm of x and norm of f equal to. Okay, next corollary, second corollary is that let x be an element of a norm space. Let x be an element of a norm space Then then there exists A belongs to B such that f(x) equal to norm x and norm of x equal to 1. Here, here we talk about that let let z belongs to bx, okay, with norm z equal to 1, then then gx less than equal to norm of z of x, then this one norm g equal to 1, this implies norm of x, hence we talk about, we just not here just taking modulus since g be functional is for range is k, so we just talked about this one mod. So we talk now taking supremum of mod of cx, x belongs to x star, means increase this domain and null of z equal to less than equal to null of x marked as 1, and obviously in this way we see that, note that norm of x equal to norm of equal to gx. If we talk about gx, then this gx less than equal to mod of gx. This implies that norm of x less than equal to supremum of x belongs to x star mod of x equal to 1 and normal x. Okay, this marked as true. Then what we find from 1 and 2? From 1 and 2 we get norm of x equal to supremum of g of x, where x belongs to x star and norm x equal to 1. Okay, we get this conclusion also. So with just this problem, we write these two problem of application of Hahn Banach theorem and obviously getting some corollaries from this problem. So today we stop here.